Hello, Calc 1 students. As I mentioned this morning, I was not happy with the presentation that I gave with regard to derivatives of inverse functions. And so I want to take another crack at it here and give you a short presentation that will hopefully clear up some of the things that we went over this morning. So let's get at it. I'm going to go ahead and turn off my video and share my screen and try to make this relatively quick, but hopefully effective. So you should be seeing on your screen a document that I've put together. I'll also post this in Canvas. And it's titled Derivatives of Inverse Functions Synopsis. So what I'm trying to do here is synthesize the main concepts of finding derivatives of inverse functions with a few examples. Okay, so we'll kind of read through this and look over these examples, and hopefully it will give you a better idea of what's going on. So you can see I've used Desmos to help me. So I write here, recall that inverse functions have symmetry about the y-axis. So that in this drawing is the green line, right? And so what that really means is for any xy pair that's on f of x, right, the yx pair will be on the inverse function. So for example, in this series of functions that I've put in Desmos, my main function f of x is going to be 2x squared. All right. The point 1, 2 is on f of x. The inverse function winds up being the square root of x over 2. Right? That's this blue curve, right? So the red curve is 2x squared. The inverse function, this blue curve, is the square root of x over 2. So notice the point 1, 2 is on f of x, and the point 2, 1 is the mirror image on the inverse function of x. Okay, so that's basically what we mean by inverses. We swap the x's and the y's. So in general, if I have some point AB on f of x, then BA will be on f inverse of x. Now, what if I were to draw a line tangent to f of x at some given point? So in this example, in the generic sense, right, if I'm looking at AB on f of x, then if I'm interested specifically in that point AB, then that means f of A would be B, right? So in this example, A would be 1, B would be 2. And it has, so the tangent line to that curve will have some slope, right? So f prime of A will have some slope to it, which in general, we're just going to call P over Q. All right, change in Y over the change in X. In the example you see on Desmos, the derivative to 2x squared, which is 4x, will have a slope of 4. So this tangent line here, it's another blue curve or blue line, tangent to f of x at the point 1, 2 has a slope of 4. So the P over Q you could consider to be 4 over 1. There will be a mirror tangent line to f inverse of B, which will equal A, right? So in other words, if AB is on f of x, then BA is the mirror image on f inverse. On this drawing, that's the point 2, 1 on my square root of x curve, right? The slope of this tangent line, again, think about it this way, the x's and the y's are reversed. So if the slope of the tangent line to f of x is 4 over 1, then the slope of this tangent line to f inverse of x at 2, 1 will be the reciprocal, right? Q over P. Well, if P over Q was 4 over 1, then Q over P will be 1/4. And in fact, that's what it is. So this black line represents the tangent line to the curve of F inverse of X at 2, 1. That's basically, I mean, if you understand that, you've got most of this lesson. So if the point 1, 2 is on F of X, that means if F of X has an inverse function, then the inverse function will have a point 2, 1 with it. If the slope of the tangent line to F of X at 1, 2 is 4, then the slope of the tangent line to the inverse function at 2, 1 will be 1 over 4. That's pretty much it. Okay. And so that's what I've shown here, where F of X is 2x squared. That's this red curve. The inverse function, square root of X over 2, is this blue curve. And I've got the tangent lines to both. They have reciprocal slopes. Everything is mirrored to y equals x. Okay? So where does our formula come into play? The formula essentially says what we just talked about. It says that if the derivative, if we're talking about finding the derivative of the inverse function, which would be this blue curve, right? At B, well, what is B? What do they mean by B? This is where I think I had some mix-ups and problems this morning. B, right? The input for the inverse function will be the output of the original function. So in this example, B will be 2. It will be the output of F of 1. So F of 1 is 2. So B on the inverse function will also be 2. So if I want to know what the derivative of the inverse function at B is, right? We can use that inverse relationship of slopes to say that will equal 1 over the derivative of F evaluated at the inverse function of B. Okay? Because remember, what does this mean? F inverse of B, F inverse of B is A, right? F inverse of B is A, right? There's that inverse relationship. So the input of F gives you an output of B. That means then the inverse function evaluated at B will give you A back. So we swap values. Okay. So what does that mean in the long run? How could we use this formula to help us? If I want to know what is the slope of my inverse function, square root of X over 2, evaluated at 2, right? And let's say I don't really understand, maybe I don't know how to take this derivative, but I do know the inverse function is 2x squared. Okay, so if I want to know the derivative of X over 2, or the square root of X over 2 evaluated at 2, that would be the reciprocal of the derivative of the inverse function 2x squared evaluated at 1. Well, what would that be? Well, the derivative of 2x squared is 4x. So if I want to find the derivative of the inverse function evaluated at 2, then I need to first find the derivative of 2x squared evaluated at 1. Well, what is that? That's 4, right? Derivative of 2x squared is 4x. 4 times 1 is 4. the reciprocal is 1/4. And that's exactly what we have. So when would we use this? When would we use this? I would say this note here that I make, in general, we're not going to use it for all situations, right? And now what I'm saying in this paragraph here is, in general, using this formula to find the derivative of an inverse function is probably not going to be that helpful, because the first thing you have to do is find f inverse itself. Well, that can be challenging, if not impossible. And we looked at a couple of examples this morning, right, where it's very difficult to isolate y when we're trying to find a function's inverse. Moreover, even if I can solve it, why wouldn't I just then take the derivative of f inverse, right? So we're not going to use this formula very often to find the general derivative of an inverse function, right? But what we can use it for, that's what this next paragraph talks about, what we can use it for is to find derivatives of specific values of an inverse function, especially if we don't know how to find the inverse function itself, right? It's not necessary to find f inverse of x, right? As long as we know that there should be an inverse of a function at some given point, right? And I can identify the derivative of the original function at a given point, I basically have to take the inverse, and that will give me the derivative of the inverse function at that given point. Okay, where you have to be careful is what's A and what's B. Remember, in the original discussion, we talked about the point AB being on f of x. Well, if you're interested in finding the derivative of an inverse function, you've got to remember to swap the x and y values. So the B and the A would flip. So stated another way, if I want to know what is the derivative of an inverse function at B comma A, then I need to find the derivative of f of x evaluated at A. Got it? Okay. So let's look at another example, right? If we look at x squared, well, actually, I'm going to let you read through this because this is very similar to my example above, because I'd look at 2x squared versus just x squared. So this is just another example where I show you that you can do this derivative two ways, right? If you can easily find the derivative of f of x, I'm sorry, the inverse of f of x, then just take the derivative of the inverse function and you're good to go, right? You can also use the formula to get to the same conclusion. So in this example, I'll let you read through it, but if we want to find, given that f of x is x squared, and we want to find the derivative of f inverse evaluated at 4, right? We can either first find the inverse function of x squared, which winds up being square root of x, take its derivative at 4, and you're done. Or you can use the formula, which really is a little bit trickier, because you got to remember to swap your x's and your y's, right? So what we'll wind up doing is find the derivative of f of x, right, evaluated at 2. Okay. So in other words, if you plug in, if you want to know f inverse of 4, right, we need to find the value. We need to set x squared equal to 4, because that will be the input for f inverse will be the output for f of x. So we set 4 equal to x squared, right? And we get plus or minus 2, but assuming we're working with 2, right, then we would say, what is f prime of 2? F prime of 2 is 4. So the derivative of the inverse at that same point would be 1 over 4. And here's a picture. So at the point 2, 4, right, on f of x, which is x squared, you can see the slope here, right, would be 4. And at the point 4, 2, the slope will be the reciprocal, which is 1/4. So where can we actually use it, though, to our benefit? Because, right, in that previous example, we really didn't need to use the formula to find it. What about something like number 2 or paragraph 2 here, where we're looking at finding the inverse or the derivative of the inverse function of x plus square root of x evaluated at 2. Okay. We could, with piecewise functions, find the inverse of f of x, but it's not going to be just a nice simple swap the x's, swap the y's, solve for y, right? There's going to be some extra work. And the point is we don't even really need to know what it is. So in this case, because it's not simple to simply find the inverse function of x, of f of x, we can use the formula. We can say, okay, if I want to know what is the derivative of f inverse evaluated at 2, well, that means f of x itself must be 2. So what values of x will yield 2? Okay, so in other words, we have to solve 2 equals x plus square root of x, right? So as I note here, we could solve this algebraically by isolating the square root of x, squaring by both sides, and you know, continuing to work it algebraically. Or you can quickly look, right? Sometimes it's just fairly obvious, right? 1 is definitely a solution. X equals 1 is clearly a solution, right? So we're going to go with 1. We know that that works. In other words, the point 1, 2 will be on f of x. The point 2, 1 will be on inverse f of x. So all we need to do now is find the derivative of f evaluated at x equals 1. Take the reciprocal, and that's the slope of the inverse function, or the tangent line to the inverse function at 2. So derivative of f of x is 1 plus 1 over 2 root x. We substitute in 1. So f prime of 1 winds up being 3/2, which means the derivative of the inverse function evaluated at 2 is the reciprocal, 2/3. And we're done. And what I've done in this last drawing, and then I'm going to turn off this recording, is I've graphed the function x plus square root of x. I've graphed the tangent line to the curve at the point 1, 2. I put in my y equals x line for good measure to show you the inverse relationship. So we know if 1, 2 is on the graph of f of x, the point 2, 1 will be on the graph of its inverse function. But most importantly, I can graph the tangent line. I know what the tangent line is to the curve of f inverse of x evaluated at 2, 1 without even knowing what the curve looks like. I don't even know what the function is, but I know what the tangent line is. It's right here. 2/3 x minus 1/3, right? How do I know that? Well, I know that 2, 1 has to be on the curve because 1, 2 is on the inverse function. I know that the slope of the tangent line has to be 2/3 because the slope of the tangent line to f of x is 3/2. So by using the point 2,1 and the slope of 2/3, I can find the y-intercept to be -1/3. There it is. So if you look carefully, this purple line has symmetry to y equals x with this blue line. So every point on this purple line, swap the x and y values and you'll have a mirror image on the blue line. All right. So I'm going to leave it there. I hope that helps a little bit. And again, please let me know if you have questions and I will try to clear them up. All right. Take care.